current at beta is 0, so we find that one.
For finding beta, I mean, I did not mention the expression. So the question is for this, let me make sure I understand the question correctly. If you have a controlled full wave rectifier with an RL load, how is it that we are going to be able to find this beta, right? Is that your question? All right. So the expression is similar to the expression that we have had in the past. So remember when we were analyzing half wave rectifiers, let me see if I can find it. Like this beta that we had earlier here for a half wave rectifier, and we had like an expression. So beta is like the solution to like a very large, expression like this. We can use the same thing over here. So it's the same expression because as it turns out, we have like a sequence of half cycle exciting and RL low. So it doesn't matter if it is a half wave or a full wave, you're still going to get the same equation for solving beta. Yeah. Other questions? Okay. So what we did last time was we are still in chapter 4. Chapter 4 covers full wave rectifiers, and we started with a full bridge and then a center tap resistive load kind of a rectifier, and we kind of expanded that with a resistive load placed in series with an inductive load. And then we looked at a case, what if we have a capacitor placed in parallel with the resistive load? And then we looked at a case where we have a controlled full wave rectifier, meaning that instead of the diodes, we are replacing them with SCRs. And as it turns out, we have two kind of different modes of operation when it comes to an RL load. If the inductor is relatively small, the current is going to be discontinuous, like over here. You can see this is the output current. So this is the firing angle of your SCR. The current conducts, but returns back to 0 at beta before the next firing angle arrives, before pi plus alpha arrives. And as you can see, and we analyzed last time, for instance, your output current is discontinuous, like you see over here, and this solid, thicker line over here is your output voltage. So please note that your output voltage at some instances is even negative, like over here, from pi to beta, the output voltage is negative. So we just had a question about how to find beta, and beta would be the answer to, I don't know if there is an equation here. We don't have an equation here, but I just explained in a half wave rectifier how to find beta. You can use the same equation. And there might be a case that either your inductor is relatively large or alpha is relatively small, the firing angle is relatively small. So as you can see, the inductor current does not have a chance to return back to 0 before the next firing arrives. So basically, you are going to observe that you have kind of a continuous output current waveform, and your output voltage waveform is not sitting on 0 anymore. It's either following the input voltage or the negative of the input voltage. And as you can see, your output voltage at the beginning is negative, and then you trigger the next SCR. It follows the positive path, then becomes negative again. Then you follow the next pair of SCRs, and then it follows the positive and then becomes negative, and we have a sequence like that. Let me see if the equation is here. I guess not. I will mention it. So the question is, how do we know if it is operating in continuous conduction mode or discontinuous conduction mode? There is an expression in my notes as well as in the book, and the expression was mentioned over here. Like if alpha is less than the inverse tangent of L omega over R, you're pretty much guaranteed that you are in the continuous, basically, conduction mode. All right, going back to the PowerPoint. As it turns out, somebody who had plenty of time has, if you look at the output voltage waveform in this case, which is basically this curve over here, it's a periodic waveform. So again, you can go back to the Fourier, series and say, I want to break it down to its harmonics. Somebody has done this, and this is the result of that. So AN and BN are the components of your Fourier series, and N is the order of the harmonic that you're interested. As it turns out, because of the symmetry in the system, you only have non-zero harmonics at N equals to 2, 4, 6, and so forth. So for instance, you don't have a harmonic at N equals to 3. Once you find AN and BN, then you can actually kind of, get the square value of them and then add them with each other and get the square root of the whole thing. And then you can get Vn. Vn is the magnitude of the nth harmonic of the output voltage, basically. N being 2 and 4 and 6. And if you're interested in L equal to 0, which is your DC harmonic or DC component, it's actually given over here, which is 2Vm over pi times cosine of alpha. So this is kind of a breakdown, a Fourier breakdown of this waveform as our output voltage. So if you're interested in, for instance, looking at, RMS values, filtering effects, looking at how it's going to impact some sort of a load, similar to what we did before, you can use superposition, apply each one of these harmonics, look at your response, and as long as your system is linear, you can add all of the responses together to find the overall response. So there is a Fourier actually series represented over here as well if you're interested in working with that. Then the rest is kind of simulation stuff appears in the book. And then the book goes on and assumes that what if there is a DC source also appearing on the output side. We are not going to analyze that. And what we are going to analyze today is a three-phase, basically, rectifier. Before I do so, just a reminder, we are going to have a quiz on Tuesday, and the material that is going to be covered in the quiz is half-wave rectifiers, okay, which is pretty much everything that we have covered in class appears in Chapter 3 of the book. That doesn't mean everything that appears in Chapter 3 of the book we have covered in class, so there is a difference. So half-wave rectifier quiz next week on Tuesday. So we are going to start talking about three-phase rectifiers. So the first question is, why three-phase? What is wrong with single-phase? The answer would be, whenever you want to consume higher amounts of power, you want to actually kind of consume this load in a three-phase balanced kind of a approach instead of having a single-phase approach, because otherwise the power utility people are going to have a hard time balancing out their load. The other advantages are, for instance, in a three-phase system, the instantaneous value of the power that you can absorb from the grid, as long as this is a balanced grid and everything is symmetric and ideal, is constant. So in a single-phase system, your instantaneous value of power is actually having a kind of a fluctuation of 120 hertz, versus in a three-phase system, there's no harmonics in your actually instantaneous value of power. So instantaneous value of the power and average value of the power in this three-phase system are basically the same. That's why, for instance, that's the reason a three-phase motor is going to have less vibration, or, for instance, it injects less harmonics in the grid and things like that. So whenever your power that you're trying to absorb is, for instance, more than 500 watts or maybe 1 kilowatts or maybe 2 or 3 kilowatts, you better go and consume that power in a three-phase fashion. The other reason that we are going to see later is if you look at the rectifiers, for instance, if you have a capacitor in parallel with the resistive load that you have in a full bridge single-phase rectifier, the maximum voltage that you can obtain equals the maximum DC voltage on the output side that you can obtain equals the peak value of the input voltage. As it turns out, if you want to go beyond that maximum value that the single phase can offer you, you got to go to a three-phase system, and in that case, the maximum value of the voltage is the square root of 3 times the peak value of the line to neutral voltage. So that would be another incentive for us to go for after a three-phase basically system. So what we are going to do today is look at this guy. We are using 6 diodes. Each pair of diodes are covering one phase. And then we are going to look at briefly look at a controlled three-phase rectifier, meaning that the diodes are replaced with SCR. So basically you have a little bit of a control over the DC level of your output voltage. And I think that's pretty much it, as long as we are concerned about this chapter number 4. All right. Any questions? All right. So let's go to one note. So we have to introduce a three-phase system. So first of all, our topology is like this. We have three phases, VA, VB, VC. In this particular case, they are kind of Y connected. And obviously, each one of them has 120 degrees of phase shift from the other one. And then we have D1 and D4 covering phase A, D3 and D6 are covering phase B, and D5 and D2 are covering phase C, the third phase. Please note that the order that these diodes are numbered are kind of important. If you just number them like this is 1, 2, 3, and then 4, 5, 6. Nothing is wrong with that, but as it turns out, if you order it this way, I just wrote on the board with a red pencil, it's kind of hard to imagine what diode is going to conduct after the other one. So please pay attention that the order that these diodes have been numbered turns out to be important later. All right. The reason is first D1 conducts, first D1 and D2 conduct, then D2 and D3 conduct, then D3 and D4 conduct, something like that. So this order is important. So let's look at our three-phase system, and even before doing so, okay, yeah, let's look at this. So we have phase A voltage. That's the line to neutral voltage of phase A. And then I hope you guys are not colorblind. It's going to be a little bit of a problem. Oops, I don't know how to make this a little thin though. I don't know. I was hoping I could use all colors, but looks like some of them are thicker than the others. So let's do this one. And finally, blue, let's call it phase C. So like RGB, red, green, blue of like a TV kind of a signal. I'm just following almost the same pattern. All right. So assuming that this is the omega t, this is my time. So we're looking at 0 to 2 pi. So this is one period, and then I'm actually looking at 2 periods of my signal, okay? As you can see, sometimes VA is larger than VB, and it is larger than VC. For instance, if you look at this particular time instance, you can see that VA is larger than VB. VB is here, and it is larger than VC. Then the game changes. For instance, later on, for instance, at this time instant, VB is larger than VA, and it is also larger than VC. So it's like these three voltages are wrestling with each other, which one of them is going to be larger. So have this in mind and consider a circuit like this. Let's say we have a case like this. We have three sources. Okay, let's call it, this one is 10 volts. And this one is, let's say, 5 volts. And this one is, I don't know, negative 2 volts. And they are all okay, and they are supposed to provide power, if allowed, to a resistive load. So if you have like 3 diodes over here kind of placed in parallel, each one of them on the anode side are being fed by a voltage source, and on the cathode side they are all connected to each other, and ultimately a resistor, and ultimately a loop. So over here you can argue that between these two, if you want to analyze which one of these diodes is going to be on and which one is going to be off, as it turns out we have 3 diodes. Each diode has 2 possibilities of being on or off, so totally we are looking at 8 possibilities. As it turns out, only one of them is a viable possibility, and that is when this guy is on and the other 2 are off. All right? Because if the diode that is connected to the higher voltage is on, then you can successfully argue that the other 2 diodes are reversed biased, no problem, they are off, they are not conducting. So if you have a configuration like this, the diode that has an anode which is connected to the highest voltage is going to win and conduct. So if I change the configuration and say, okay, instead of 2 volts, I change this voltage and change it to, let's say, 20 volts. All right? Now the bottom diode is connected to the highest voltage. The anode of the bottom diode is connected to the highest voltage. So this conduction is going to change to, I don't know why I cannot erase this, but okay. This being on and the other two being off. All right? If you assume different than this, you're going to basically end up having a contradiction. All right, so keep this in mind. Another thing that I want to mention is kind of similar to this, just a little bit different, and that would be all right, what if you have a configuration like this? I'm not changing the polarity of these sources, but I'm assigning them a negative voltage, like negative 10 volts, negative 5 volts, negative 15 volts, something like this. And then I am doing something like this. Let me see if I have enough space. All right. All right, so let's say argue that we have a configuration like this. All right. Again, I have 3 sources. They're all negative, and then 3 cathodes of 3 diodes are actually connected to the negative terminal of the sources, and they are actually hooking up to each other, creating 3 loops, feeding a resistive load. Now, in this case, you can argue that the diode that is connected to the most negative source of voltage is going to conduct. So this is going to be on, and the other 2 are going to be off. All right? So if you have a configuration like this, they are going to be basically connected to the lowest voltage. Okay. Or maybe I think I wrote this in a wrong way. Let me redraw this circuit one more time. Okay, sorry. I think this is not the right way of presenting this. So we still have 3 sources. And then we have 3 diodes. Let me just do it this way. All right, one side of the diode is connected to a resistor, and this is still connected here. And these diodes are connected to, let's take this all the way down to here. All right, let's say if you have a system like this, a little bit different than what I earlier drew. In a system like this, the diode that is connected to the most negative voltage is going to conduct. In this case, we have negative 10, negative 5, negative 15. This is the most negative one. Therefore, this diode is going to conduct, and the other 2 are going to be reverse biased. If the situation changes, for instance, this negative 5 changes to 5, then the new numbers that we have negative 10, negative 5, and 5, and negative 10 is the most negative one. So then this diode is going to conduct. Okay? All right. So if you look at a 3-phase system, it's a combination of both of them, basically. If you consider these 2, let me just zoom out a little bit. All right. If you kind of combine these 2 networks with each other, you're going to end up having something like this. So we have these 3 diodes that are competing to conduct, and the winner is whichever is connected to the highest voltage. So we have to observe VN, VAN, VBN, VCN, and see which one of them is the largest one, and whichever diode that is connected to that largest one is going to conduct. Then it comes down to these 3 diodes. And between these three, the winner is whichever is connected to the maximum negative voltage. Okay? So keep that in mind. And let's actually draw a bunch of waveforms. So let me kind of copy this and bring it maybe, make this a little smaller. All right, insert. All right, kind of want to have all of them on the same screen, but looks like things are going to get a little small. Okay, all right. So let's observe these voltages and see which one is the largest one and then make a decision. So as you can see, if I want to make a decision between D1, D3, and D5, I have to see which one of them is connected to the highest voltage. For instance, from here to here, VAN is the largest one. Remember, red one is the VAN. That means D1 is going to be on. Okay? So this is starting from here all the way down to here. Then after this point, the green one is the largest one, and green was VBN. So if you look at the schematic, D3 is connected to VBN. So from here to here, D3 is going to be on. Then for the third portion of the cycle, we have the blue voltage, which is VCN is the largest one. And D5 is connected to the blue, basically, voltage source, so D5 is going to be on. And we just covered one cycle. Then the next cycle will start. Again, the red one, which is VAN, is the largest one. So D1 is going to be on, then D3, and then D5. Okay? All right. So this is as long as the top diodes are concerned. All right. So, by the way, remember, each one of these diodes that are going to conduct, they are going to clamp this node to the voltage source. So basically, if you're observing the voltage of this particular point with respect to this ground, the neutral point, it is going to be like a curve like this. Okay? All right. Now, what about the voltage of basically this negative point with respect to the neutral point? Neutral point is actually here, the neutral point of our three-phase system. All right. So again, we have three diodes that are competing, D2, 4, and 6. And between these three, the winner is whichever that is connected to the most negative voltage. So we have to look at the negative side. For instance, here in this time interval, you can observe that VCN is the largest one, right? So which diode is connected to VCN? That's diode number 2. So D2 is going to be on. All right. Then the red curve is the most negative one, and red one was VAN, and VAN is connected to D4. So this is going to be D4. And then green one is the most negative one, and the green one is VBN, and VBN, according to the graph, the schematic, is connected to D6, so D6 is going to be on. And then the cycle repeats, then D2, then D4, and then D6. All right. So if you have like an oscilloscope or whatever and measuring the voltage of the negative terminal over here with respect to the negative terminal of our load with respect to the neutral point of the source, you will be observing a voltage like this. All right, something like this. Now, the output voltage is the voltage of this point with respect to the neutral point minus the voltage of the negative terminal with respect to the negative to the neutral point. So technically, if I get the difference between these two kind of traces, the top trace over here and the bottom trace over here, that is going to be my output voltage from positive to the negative terminals of the load. That's how I've defined my output voltage. Okay, so let's do it. So let's try plotting that. Let me create a little bit more space here. All right, so let's zoom out now. Zoom in, I'm sorry. Okay. Okay, so let's focus here, for instance. This is too much, maybe. Okay, so let's focus, for instance, in this time interval. Okay, okay. The positive terminal of the load is following VAN, and the negative terminal of the load is following VCN, okay? I'm sorry, VBN. So the output voltage is VAN minus VBN. So over here I have Vout. Which one was that? The green is red. BN, right? The green is BN. Okay. VAN minus VBN is like the line-to-line frequency of my source, which is VAB. Okay? All right. So in this particular interval, I have to follow VAB to identify my output voltage. All right? And, all right. If you plot VAB, VAB is going to look like this, basically. So I kind of have to look at the line-to-line voltages to be able to plot my output voltage. Let's take another example. For instance, let's do here. All right. On the positive terminal, I'm following the green curve, and the green curve is VBN. On the bottom side, I'm following the red curve, and the red curve was VAN. Well, as it turns out, this is the opposite of that, VAN. So Vout is VBA, which is the opposite of VAB, basically, okay? Now let's take another one. Hopefully this is not going to be very similar to what we just did. Let's consider this time interval. Okay? On the positive side, the blue curve is the winning one. D5 is the one that is conducting, and that is VCN. Minus, on the bottom one, I'm following the green curve, which is D3, which is D6 conducting, and that would be VBN. So my output voltage is following VCB. All right? So if you do it for all these 6 intervals, so we have actually 6 intervals, you're going to realize that you're constantly following one of these line-to-line voltages. So you have to go back and plot these line-to-line voltages that I have plotted over here. I hope, again, you're not colorblind. And then, as it turns out, for instance, this would be VAB. The next one will be VAC. Then VBC, then VBA, then VCA, and then VCB. And again, VAB appears, meaning that we are done with one period, and this cycle repeats itself, okay? So let's take a look. In this particular time interval, I was supposed to follow VAB, and VAB is actually here. So I'm following this. All right? Then in the next one we did, okay, let's look at one that we have already analyzed, for instance, in this time interval. We are supposed to, V out is VBA, and as it turns out, VBA is the largest one. Let's look at this one too. Okay, what happened? VCB. We were supposed to follow VCB, and this is VCB. So if you do it for all of these intervals, you're going to realize that you're kind of following the peak values or the envelope of these line-to-line voltages. So this is going to be your V out. Okay? All right. So several notations. First of all, our V out is a very good DC signal. It doesn't have a lot of ripple. You know, if you compare it with all the single phase rectifiers that we have had, oops, something happened here. I don't know why this thing moved. Let's just erase it a little bit and then do it again. Uh-oh. Okay. I have no idea what's going on, but anyway, where is this 5 coming from? Anyway, let me read off the output voltage, okay? This is going to be our output voltage. Okay? So if you look at a sequence, the output voltage first follows VAB, then VAC, then VBC, VBA, VCA, and VCB. Okay. Several notes. The output voltage is relatively DC. It doesn't have a lot of ripple. See the ripple. We just have a tiny little ripple over here. And please remember, this is just we use the resistor as our load. We did not even try to make it fancier using an inductor in series with the load or using a capacitor in parallel with the load. It is actually still a good DC signal, even though our load is a purely resistive load. So that's one note. The other one is, if you look at the ripple or the frequency of the ripple that appears in your output voltage, it is 6 times the ripple of the input voltage. So if you look at one period of the input voltage, if you scroll up, let's say from here to here is one period of my line voltage. As it turns out, the output voltage is kind of repeating itself 6 times during that period. So this would be one period of my line voltage. 1, 2, 3, 4, 5, 6. And you can see within this one period of the line voltage, the output voltage has repeated itself 6 times. So the frequency of the ripple is 6 times the line frequency. Like if the line frequency is 60 hertz, the ripple is 360 hertz. So it's easier to filter that out. So that's another advantage. The other thing that I wanted to point out and goes back to the conduction of the diode. So you can see in this time interval, D1, among the top diodes, D1 is the one that is conducting. Among the bottom diodes, D6 is the one that is conducting. Then the next interval, like here, D1 still conducts, and then D2 conducts. So if you kind of look at the sequence of the conduction of the diodes, you're going to see D1 and D2 conduct. Then D2 and D3 conduct. And then D3 and D4 are going to conduct. And then D4 and D5. And then D5 and D6. And then D6 and D1. So it's like a circle of how the diodes. So at any given time, only 2 of the diodes are conducting. One on top and one in the bottom. And this is the sequence. So that actually is why we are kind of numbering these diodes in this fashion of 1, 3, 5, 2, 6, 4, because when it comes to arguing about their conduction, it's very easy. So I know that these two conduct, 1 and 2. Then 2 and 3 conduct. Then 3 and 4 conduct. Then 4 and 5 conduct. Then 5 and 6 conduct. So just looking at it, I can easily say that. All right. All right. So this is our output voltage waveform. Let's say you're interested in a bunch of other waveforms. For instance, the voltage drop across D1. Okay, let's look at the voltage drop across D1. Now I'm going to use a different color, and hopefully things don't move. And okay. First thing that you can tell is whenever the diode is on, the voltage drop across the diode is 0, okay? So if you look at the conduction period of D1, which was here, and also here, I just have to plot 0, okay? So let me just do that. And that would be here. And it's really hard to make a judgment, but I think it's here. So I'm trying to draw a voltage drop across D1, okay? Then, as it turns out, it's actually following the maximum value of the voltages. So I'm just going to plot it and then explain it later, okay? Or maybe I can explain. Oh, maybe I can plot it first. Okay, so this is going to be voltage drop across a diode. Remember, whenever you are plotting the voltage drop across a diode, it should either be 0 or negative. This is the case here. And whenever the diode is blocking a voltage, the peak voltage that it has to block is the peak value of the line-to-line voltage. So for all of this is true for all of the diodes. So VD, any diode, maximum value is V line-to-line maximum value. Okay? So whatever your line-to-line voltage is, you should be able to buy a diode that can handle that part of that amount of negative voltage drop. If you want to know what happens, for instance, after the diode is, why is it that we are, for instance, following, let me see, VAB. This was VAB, right? Why is it that when we turn the diode off, it is following VAB up to this point? The reason is because D3 is getting on after that. And if you look at D3 being on, and you look at this voltage drop, I'm sorry, the other way around. If you look at the voltage drop across this diode, you got to look at this loop basically. Okay? So you're looking at VAN and VBN involved, so you have BN involved, so you have to get their differences. So this gives you this curve basically over here. And then beyond that, D5 is the one that is conducting, right? So if I erase all of this, so if D5 is on, you have to basically look at this loop now. To find the voltage drop across D1, and that would be V, for instance, AC or CN or something like that, and that would be given here basically. This portion of this curve over here. All right, so this is the voltage drop across the diodes. More important than the diodes voltages are the diode currents, and please remember our load is a resistive load. So if you have the output voltage, this is also resistive value times the output current. Okay, so this also gives us the waveform for our output current. If I'm interested in plotting the current of a diode, let me do it. This is going to get a little scary. I'm just trying to copy and paste this thing down here. And make it sure it's aligned. Okay. So let's look at the Okay, so we are trying to plot the current of the diodes. So diodes have non-zero current as long as they are on and the voltage drop across them is 0. So whenever the diode is off, I'm guaranteed that the current of the diode is 0. So I know that by looking at the voltage drop on the diode, it is off here and it is off here. So all I have to do is just plot 0 here. And also here. And also here. All right. Beyond that, D1, for instance, plotting ID1. Beyond that, the diode is on, and as it turns out, whenever D1 is on, looking at the schematic, whenever D1 is on, the diode current and the load current are the same. So all I have to do is just follow the waveform of the load current. Oops. All right. All right, so this is going to be our D1 current. So this is ID1. Okay. So out of the 6 segments of our period, it, for instance, conducts out of 2 out of those 6 segments. And then you can, for instance, plot, I don't know, ID2 and D3 and things like that. And just let me make sure that I highlight the peak value of this. This would be V line to line, maximum value over the load resistance that we have. So this is the waveform of the diode. And ultimately, let's say you're curious about what is the current that is being drawn from the source. For instance, phase A, how much current, or what is the waveform of the current that is being drawn? If you are interested in that, you have to look at D1 current over here, and then D4 current over here, and then subtract them from each other. That would be your current of phase A. So I'm just going to plot it over here. All right, insert. All right. Not okay. Okay. So let me just draw it over here. So I already have ID1, and then I'm not going to find it, but let's say we already know what ID. Let me actually plot it. It may not be a bad idea. So I'm trying to plot ID1 minus ID4. D1 is here, D4 is here. If I get the subtraction, applying KCL over here, that would be the phase current of phase A. Okay, current of phase A. Okay, D4 is conducting here and also here. All right, so I have to consider that. And whenever this diode is on, it is following the current of this current of the load. So let me just plot it with a different color on the same curve. Okay. This is going to be like this. Okay, yeah, so this is an ID4. And then IA, which is the current drawn from phase A, is ID1 minus ID4. Okay, so I just have to subtract these two waveforms from each other, and that would give me, let me just use the same color. Okay, something like this. So this would be the current that you are drawing from phase A. Please note that this current is, first of all, on average is 0. The average value of this current waveform is 0. And then it's kind of symmetric. You can see it's non-zero for 2 segments out of those 6 segments of the period. Then it's 0 for 1 segment. Then it's negative for the 2 other segments. Then again, it comes back to 0. So this is in case you're interested in plotting, for instance, current of phase A. All right. Any questions so far?
So will we get a graph this in the exam of these line to line voltages?
Yes, the question is if you have been asked to plot one of these waveforms, I will provide you this kind of raw kind of waveform so you can just mark it like what I'm doing over here. I provide you with the dotted lines and then you can highlight wherever the curve follows, whatever the curve follows. Oh, yes.
What about the power factor?
The power factor. Okay, let me see if I have any information about the power factor. Is first of all relatively good because if you look at this last phase current that I draw, it's very way up here, but it's kind of in phase with my current on phase A basically. Let me see if I can I don't think I can superimpose them, but if you look at this red curve, red sinusoidal signal, which was my phase A current, it turns out it's totally in phase with this blue curve that I have here, which is my phase A current. So power factor is relatively good because they are in phase with each other. But it's not ideal because the current that we are drawing is not sinusoidal. It doesn't look like sinusoidal, but it has a very significant, actually, first harmonic content in itself. I may have some power factor information, and I don't think I have it. Okay. All right. Any other questions? So let me see what else we should be discussing as long as... okay, so... let's talk about, for instance, the average value of the output voltage. I have them in the notes. I'm just going to point them out. All right. So if you are interested in getting the average value of the output voltage, first thing that you got to note is, okay, is this waveform periodic? What is the period? And you can see the output voltage is this guy over here. And all you have to do is just to take the average value of the signal over this interval, because the rest is just a repetition of this segment. So all you have to do is just focus on 1/6 of your period and then take the average value of the output voltage, one of the basically line-to-line voltages. So that's what we are doing over here. Okay, I'm focusing on 1/6 of the period, which is from here to here, and then looking at the line-to-line voltage, which is some peak value which I highlighted as Vm line to line, d omega times sine of omega t times d omega t, and that turns out to be the average value of the output voltage is 3 times the peak value of the line-to-line voltage over pi. Okay, so this basically tells me if this is my output voltage. If you are interested in the average value of this output voltage, this would be 3 over pi, which is almost 1, because pi is very close to 3, times V line to line. Oops. Maximum value of the line-to-line, peak value of the line-to-line, times 3 over the square, 3 over pi. Also, you can see that your output voltage is a kind of a periodic waveform, so you can kind of break it down into the harmonics that it has. And we have done it over here, and here are the magnitudes of the harmonic. N is highlighting the order of the harmonic, and multiplied by 60 hertz, which is the fundamental frequency of the line. As we discussed earlier, the output voltage repeats itself 6 times in one period, so there's no wonder the first harmonic that you have is at 6, n equals to 6, which is 360 hertz, then 720 hertz, and so on and so forth. So other than these numbers, the order of that, for instance, what is the 4th order harmonic in the output voltage is 0. The first harmonic that appears after the DC component is the 6th order harmonic. And what is the amplitude of that 6th order harmonic? It's 6 times V, maximum of line to line, pi times n squared. In this case, n is 6 minus 1. And as you can see, as you go to higher orders of harmonics, because n squared appears over here, they drastically get small because there's a division by n squared. So you can see it's already kind of a self-filtering, does a good self-filtering thing to reduce the order of harmonics. The other one is, for instance, let me see, the RMS value of the diode currents and things like that, and the apparent power and things like that. Okay, so let me just rewrite the sentence that I have over here. The sentence is this: each diode okay, so we have 3 diodes on the top, and they are kind of, each one of them is conducting for 120 degrees. And we have 3 diodes in the bottom, again, each one of them is conducting for 120 degrees. So if you focus on each individual diode, they only conduct for 1/3 of the period. So on average, the current of all of the diodes are the same. If you look at the average value of these diodes, as long as this is a balanced system, all of these currents are the same, and that would be 1/3 of the output current on the average value of the output current. Again, going back to the RMS definition, you can conclude that D1 RMS equals to D2 RMS. I D1 RMS is the same as I diode number 2 RMS equals to all the way down to I diode number 6 RMS, and that would be 1 over the square root of 3 times I out RMS. What about the phase currents? So we discussed this earlier when we were plotting things, but current of phase A is ID1 minus ID6, and you can write the similar equations for current of phase B and phase C over here. 3 KCL equations. So this gives you, first of all, the observation that on average, phase currents are 0. On average, the current that you are drawing from phase A is 0. If you look at the graph, the average value of the signal is 0. So if you look at this graph that we have over here, the average value of this signal is 0. But in terms of RMS values, the RMS value of the current of phase A is the same as the RMS value of the current of phase B, also the same for phase C, and that would be the square root of 2 times the current RMS value of the diodes. So in the end, you have 2 over 3, the square value of that, times I out RMS. Okay? All right. Now, if you are interested in the apparent power, first of all, it's a 3-phase source, so you have to, for instance, and it's balanced, so you can focus on one of the phases, find the apparent power, then multiply it by 3, and that's actually what we are doing over here. I'm saying I have 3 times the apparent power of one of the sources. So this 3 appears here because this is a 3-phase system. And then in terms of apparent power, I'm looking at the RMS value of my input voltage, line to neutral, and the RMS value of the current that is drawn from that particular phase. If you write everything in terms of line to line maximum values, you're going to have an apparent power of this, a square root of 3 times the RMS value of the line to line voltage times the RMS value of phase A current, which is determined by the output current. Also, we already looked at this when we were looking at the voltage drop across a diode. The diode should be able to block a maximum of line-to-line voltage. All right. So this portion is a Fourier representation of the output voltage. We just talked about it. And then that's pretty much it. As long as the 3-phase rectifier is concerned, this is all we care about, how basically determine some of these voltage waveforms and the basic equations in terms of RMS value of a particular current, or things like that. As you can see, our output voltage and as well as the output current are relatively DC. Okay? There's not a lot of ripple on them. But let's say you are, for instance, you have a load which is very sensitive to ripples in the current, and to make that load happy, in addition to your load that you have, which is a resistive component, you have also added an inductor in series with the load. And that inductor is relatively large, so technically you're looking at a system like this. The only difference over here is I am, in addition to my resistive load, I'm adding a large inductor. And inductors that are large could be modeled or replaced by a current source. So what this inductor does is actually even further rectifies the output current. So you can argue that my output current is almost DC. Okay, instead of being like this. Instead of being this, by adding an inductor, you can even further filter it and get almost a DC current. And that means, like previously, I had ID1 looking like this. But now it almost like a square shape kind of a current. Doesn't matter. I mean, we are just further improving things. And there's a bunch of waveforms over here. If you're interested, you can take a look. There is an example over here, which we are assuming that we have a three-phase rectifier, but our load is not a resistive load, it's an RL load. And the parameters are here. I'm not going to do it because we are kind of running out of time. I mean, not that the session is about to end, but I have other stuff to cover. But you can follow through this example that we have over here. The other concept that the book covers is, so far we were only using diodes in our three-phase system. What if we use SCRs, okay? In other words, what if we focus on a controlled rectifier, okay? As it turns out, if you use a controlled rectifier, let me again borrow a bunch of waveforms from up here. Let me see what I need. Okay. Things are even going to get messier. All right, insert. Oh, all right, let me retry it. So remember, previously the diodes made their own conduction decisions, but now that we have SCRs, we can command them. For instance, if you just focus on, let me also get a clean waveform of, see, you have a schematic of a three-phase rectifier, control rectifier. All right. All right. I don't know. Okay, so let's just focus on this SCR thing over here. All right, so we have 6 SCRs replacing our 6 diodes. Now it's called a controlled rectifier because then we can determine the firing angle of these SCRs. And as it turns out, maybe I can even use this figure over here. As it turns out, for instance, if this was a diode, D1, if we had a diode over here, this diode was eligible to conduct during from here to here. All right? Because that's when phase A is the maximum phase in terms of value. But now that we have an SCR, the SCR, as soon as this time instant arrives, the SCR is forward biased. That means it's eligible to be turned on and to be triggered. So the question is when we are triggering it. So we are triggering it at this particular point. Okay? So this is I gate for SCR number 1. Before triggering it, what happens is SCR number 6 and number, let me see, SCRs number 5 and 6 are on. So we are pretty much following the voltage that we had in before. All right. Now, as soon as this SCR is turned on, it behaves like a diode. That means we have to follow VAB, which is following now. And this follows until we trigger the next SCR. So that would be, for instance, SCR number 2. All right? And this just goes on. So with the same order that these diodes were conducting over here, we plotted up here. There's this sequence of 1, then 2, then 3, then 4, then 5, then 6. Now, if an SCR is eligible to conduct, you can actually trigger it. So you first trigger number 1, then SCR number 2, then SCR number 3, then SCR number 4. So as it turns out, by doing so, instead of your output voltage looking like this, so let's say ideally, if I only had diodes, this would be my output voltage. Okay. Now, by using SCRs, you can create an output voltage that looks like this. All right, something like this. And as you can see, on average, this voltage that I just generated is a little bit smaller than the original, just purely diode, uncontrolled rectifier. So by changing the firing angle of those SCRs, I can actually control the DC value of my output voltage. So if I, for instance, increase the firing angle, let me see if I can get something. Yeah, this is too thick. Let me see. I don't know. Let's get red. I can create something like this. Okay? Or if you're going to even make it even further, you can create something like, let me see if I can get a better color. Green. So as you can see, it gives you an extra degree of freedom to control the DC value of your output voltage, basically. So this is a controlled rectifier. We are not going to spend a lot of time over here because plotting these things is going to take forever, especially if I'm not using a board on this thing. And if you are interested, take a look at the material. And if you have any questions, please let me know. And please remember, the quizzes that are addressing these problems in the material that I have covered only covers the material that I have covered. So for instance, for a controlled three-phase rectifier, we didn't cover much, so you are not expected to know much as long as the quiz is concerned. Any questions? All right. By the way, I have graded your quiz. After the class is over, we're going to step outside and I can actually hand it back to you guys. So I want to actually spend a little bit of time on going through the solution one more time. By the way, I grade the quizzes myself. The reason for that is I want to know what kind of mistakes you guys make and then kind of correct you and mention at least the mistakes back in the class. All right, so this was our quiz problem. Voltage was given, current was given for a particular component. The first part, we were looking at the average. The first part was just plot the instantaneous value of the power. Some of the students made a mistake, and instead of 36, they put 40 as the peak value of the output of the instantaneous value of power. You can argue forever. Did this jump happen before this jump or not? It doesn't really matter, but the whole thing is if you want to do from continuity, at time equal to 0, we have 9 over here, we have 0 over here. So we start from 0. Right before times equal to 3 seconds arrives, the voltage is still 9, and we are here, we are very close to 4. So the multiplication of those right before 3 happens is 36. Beyond that, you don't care. You just know that there's a sudden chance. I'm not expecting you to evaluate the instantaneous value of power at exactly time equals to 3 seconds. So this was a very common mistake. And please remember, these are all periodic. So whatever I get here, I should get the same thing over here. I had a few answers that the instantaneous value of the power in the first segment was different than the instantaneous value of the second segment, even though everything is very periodic. So that was 40 instead of 36 was a common mistake. The other one was the average power delivered to this element. All I ask you to do is take the average value of the signal over this period. Okay? Some of you gave me 3 different average values of power. One over here, then one over here, then pretty much everybody who did this approach got it wrong when they were trying to calculate it over here. So whenever signals are periodic, identify, this is your job to, maybe the period is not, I haven't mentioned over here, the period is 10 seconds, but you have to look at the waveforms that identify that the period of all of the signals is 10 seconds. Then when it comes to averaging a signal, whenever the span of the averaging is not mentioned, the default value is over one period. So what is the average value of the signal? You have to report it over one period. Just imagine you're on the phone with someone else, then you're trying to report these numbers. Okay. So finding the average value was a kind of for some of the students were kind of a headache. And the other, finding this equation was also a headache. So a lot of you did like this. So you said, for instance, P is, and by the way, from 3 to 7, everything is 0, so all I have to focus is this. All right? So for everybody, everything is correct. Then it was like this. All right. Absolutely incorrect. You have to identify
90, right?
the equation over here and then plug that in. We are not trying to take the average value of this signal. All right? My instantaneous value of power is not 36 during this interval. It is actually 12 times time. So instead of 36, you should say 12t. Okay. So identifying that equation was important. A lot of you guys did the same thing. A few of you guys did the same thing for the RMS value of the current. Whenever it came to writing this I of t equation, you just assume I of t equals 4 during that interval. But that is wrong because I of t does not look like this. It is actually a ramp. Okay. One other mistake was when it came to I of t squared. Some of you assume that I of t squared looks like this. Which is again not correct. You're multiplying 2 lines with each other. You got to get a second order thing. So basically, if I'm interested in I of t squared, it should look like this. It's a quadratic kind of a form. Okay. So that was another mistake a few of you guys made. Now the most common mistake. And I remember I exactly mentioned that in class because I knew some of you guys were going to make a mistake, was no math at all. Just look at that peak value and then divide it by the square root of 2. Okay. Please remember, when you have a sinusoidal signal, the RMS value of that, and that sinusoidal signal on average is 0, symmetric, the RMS value of that signal is the peak value over the square root of 2. Now, some of you went a little bit further and say, okay, IRMS is that peak value over the square root of 3 because this is a triangular waveform. And again, that's wrong because this is not really a triangular waveform. So you're right. If you have a triangular waveform like this, I don't know, something like this. All right? This triangular waveform is symmetric in a sense that on average it's 0. Then you can say the RMS value of the signal is kind of this peak value over the square root of 3. But this is not really the case. As you can see, our signal is 0 sometimes, and on average this signal is not even 0. Okay? So please remember, when you're trying to find the RMS value of the signal, the short answer is not whatever the peak is divided by square root of 2 or 3 or whatever form factor you can find. You really have to look at the signal, examine the signal. Always go with the fundamentals. Go with the very original definition for the RMS value of a signal. Okay. All right, so I have the quiz graded. The other thing that I usually have done in the past is on Blackboard, there is a way for me to report your grade, basically. But that's a major inconvenience because the capabilities that you have in that semi-Excel file is not as good as Microsoft Excel. What I usually do is I have my own Excel file, all of your names and student IDs and grades are there, and I usually post that to Blackboard after I eliminate your names. So technically, you can look at your student ID number and look at your grade. There's a little bit of a privacy compromise here. So if you are objecting this, let me know, send me an email and say, I don't want my grade as well as my student ID being relieved to everybody else, because everybody can see that file. And no problem, I can just take you out of that list. But in the past, we have never had a student, maybe only one exception, one student was not happy with it. But please remember, the way that I usually post the grades on Blackboard is I have an Excel file with your student ID and your grade, nothing else, not your picture, email address, none of those. And I post that on Blackboard. If you don't want that to happen to your particular case, send me an email and I will personally send you an email and report your grade to you guys. A good thing about seeing at least not other individuals have done, but the entire class has done, because you can see all of the other grades, is you can compare yourself against the performance of the other students, against the average of the class. For instance, you have got an A, then you realize, oh, you're the only one who has got an A, or maybe there's ton other students have got an A, so it's not a big deal that much. But you know, things like that. So if you have a problem with this system, let me know. And when it comes to your name, I just delete the whole line and personally send you an email and notify you about your grade. All right, this is pretty much what chapter 4 of this class is covering. There is more advanced material over here. I don't expect you guys to be good at it. There is a kind of a short chapter after this chapter, which is chapter 5, that we don't have time to cover it today, but basically what happens in this chapter is it talks about, it's called like AC voltage controllers. So what this chapter talks about is we have, for instance, a resistive load. Okay, for instance, imagine an oven, an electric oven, or an electric dryer, or an electric water heater, something like that. Most of these electric devices that their job is to create heat, they just have a purely resistive thing over there to dissipate heat. And resistors, when it comes to dissipating heat, they don't care if the signal that you're applying to them is AC or DC or has ripple or not. They don't care. They just generate their heat. At the same time, you want to have control over the amount of heat that you're generating. For instance, you're cooking something, you want to turn it up, turn it down, those kind of things. So your load doesn't care if it is the signal that is applied to them is AC or DC, so you don't really have to worry about rectification, but you worry about controlling the signal or controlling the amount of heat that you're generating. So this chapter is actually talking about this. And by the way, another example would be a light dimmer. You know, you turn up and down your light, basically. This chapter talks about them. It's an interesting concept. So this particular one could be actually a light dimmer. This is your power outlet. This is your light bulb, conventional light bulb. And these are two SCRs back to back. And by actually adjusting that knob, you're basically adjusting the firing angle of these SCRs. So we are going to briefly talk about this when we convene back on next week on Tuesday. And then we are going to very quickly move on to the next chapter, which is actually the most important, one of the most important chapters of the book, which talks about DC to DC converters. So we have a quiz on Tuesday, as well as we are going to start talking about DC to DC converters as well. All right. See you guys next week on Tuesday.
What is covered?